Okay, hello everyone. Was a 5-minute delay, so we'll end also 5 minutes later. And I hope I can manage to fit everything into the 45 minutes. So, welcome to the best is yet to come talk. The title is a bit funny and you'll see why. So, it's not a roadmap, because some of the things are a bit fuzzy. However, we'll be talking about things that we're looking into. We'll also be looking into things that we did in the past and how they relate to one another. So it's not a strict roadmap, but it kind of is supposed to give you a feeling about what we're up to. So I'm Konrad, I work on the Akka team at Lightband. I've been doing some various community things in Krakow, Poland, including the Geekon conference, which is tomorrow. So I didn't have much time to be here in Riga, sadly. And I also did the Reactive Streams TCK. Reactive Streams is getting into JDK 9 once it's finally out, and there it's going to be known as the flow interfaces. So, maybe a quick show of hands. Who actually knows what Akka is? Who's actually used Akka? Like half of the people that raised their hand. Okay. And if you used it with Scala or with Java? Scala? Java? Okay, so half-half. So I did a mix, because I didn't quite know what to expect. And it's gonna be a mini story here, and the general kind of idea behind it is really the team motto is, okay, there's this thing, can we do better than that? Can we improve the status quo somehow? But also a personal motto that I somehow, in recent years, when people start doing reactive, I don't know, a new framework starts to do some reactive stuff, we've been there, we've done that, and some things don't work, some things do. So this is kind of why we start with the past in this talk, even though it's a look in the future. So, reactive and a ton of its meanings. I wrote a mini book, it's available for free, you can just download it from O'Reilly. But generally speaking, the reactive manifesto, everybody's seen it far too many times. Yeah, on Java conferences, like far too many times. I've been on some not so JVM focused conferences and people were a bit surprised, oh, what is that? But in the Java ecosystem, you pretty much know what this is about. It's about building resilient, responsive applications, and how do we get there. So, one tiny bit to notice here is though that, okay, there's reactive applications. Okay, so the single app is doing something reactive. So it will be good at resource utilization. For example, a single HTTP server can be good at resource utilization, handling many connections by virtue of being reactive. However, the entire system, so it can be a cluster, but doesn't have to be. It can just be multiple microservices talking to one another. They can also be reactive in the sense of being able to recover from failure, react to certain spikes in load by scaling up or down, etc. And an interesting thing to remember here is that we have these two worlds. Okay, one is the outside world, and everybody expects my API to talk JSON over HTTP. And that's kind of okay, but internally, when we have our application and our ecosystem and our company, etc., we can do actually things that are either way faster or more maintainable or more type safe, etc., etc. So there's different trade-offs between these two things. Some people would tell you to do everything via JSON and HTTP, etc. I think that's an overhead. It's a choice. I mean, if you want to, you can, but let's think about this inside part once we get into the Akka specifics. For people who have never seen Akka, the one-sentence pitch is just making developing concurrent and distributed apps simple. It's not super simple, it's distributed computing after all, but it's way simpler than without. The core of everything is really message-driven, so it's passing messages, it's not remote procedure calls, it's passing messages, which is a bit easier to both think about, because, okay, I take the message, it's getting serialized, I put it on the wire, it's getting deserialized, and it kind of matches what we really have on the network, which is, packets. A bunch of projects, but we'll actually talk about them in depth today. And the funny thing, I don't know why, but people sometimes think we only have Scala APIs. We spend a lot of time, I spent like 3 months doing only Java APIs for HTTP, so they would be awesome. So even if you're not a Scala guy, you can totally use Akka from Java. So, journey from the past. We start out 2009. It's gonna be basically a mini journey through all the modules, but like I said, it's kind of accidental that we go historically, but you'll see why, because one thing leads to another. Because when we build one thing, then we need to think about, okay, what's the next logical step to kind of improve the ecosystem. So the first thing was obviously Jonas 2009, starts with Akka. He basically wanted Erlang-like features, but on the JVM, then noticed that Scala is a pretty nice language and started writing it like that. At the core of everything, actor model. So an actor is, maybe a quick show of hands, do I need to explain what an actor is? Yes? No? I don't. So just very quickly. So you send messages or you create actors, and you always react to getting a message. It doesn't just magically do something. It's always in reaction to getting a message. So, this is what it looks like. This is actually a more, not like a hello world example, but like a real example. You have some logging here, you have lifecycle hooks, and this is the actual receiving of a message. So when I get a received temperature, I can reply respond temperature. Not very exciting, but that's already asynchronous and kind of shows off the APIs. So, the same in Java. That's actually a new thing, so that's why I wanted to show it. We recently improved all of the APIs to be a bit more Java 8 friendly. So now you have a receive builder, and you can kind of emulate what you have in Scala with pattern matching. So at the core of everything you have supervision, but let me jump ahead, because I didn't know if people would know actors or not, so there's a few really simple things here. So, important thing, you'd never expose the actor, you expose the actor ref. So it's even more encapsulated than just object-oriented with doing, I don't know, a private field or a protected field. It really is impossible to reach into an actor's state, because other people have never gotten the actor. They have always gotten the actor ref. And we do binary protocols. Right? Nowadays, maybe less scary, especially with HTTP2 around. People have gotten used to, okay, binary is actually way more efficient, so let's do that. And this is just an example of why we do binary protocols. Right? So with protobuf, that's the size of a message. I'll show you the exact message. And with Java serialization, you get like a 4x. And deserialization time is way much more than that. So, why is Java serialization so slow? Because for one, it's never designed for a high performance setting. So it's a bit bloated, and just the code for serializing, deserializing isn't so fast. Funnily enough, serializing this as an XML object would be already more efficient because it doesn't carry the names of stuff. JSON a bit smaller, and binary even smaller. Okay. So why am I talking about this? I figured I'll show you stuff you probably have not seen before. I mean, that Java serialization isn't so good, you've maybe heard, but maybe you haven't heard about this setting that we have. That's basically disallowing Java serialization completely. That's good for two reasons. One is performance, the other one is just security. Right? There's a ton of attacks on Java serialization by just loading a random class and weaving something and doing whatever people want with your system. Then you can completely disable it. Then we do some fancy stuff to disable it. So if you disable Java serialization and you do message passing, you need to somehow serialize the messages, right? So it's actually not that difficult to serialize messages with, for example, Cryo. You just need to basically configure it and then say, okay, these things that extend from that type. So you could have like a parent type, or you could list all of them here. Should be serialized using this serializer. Simple enough. So that's actual basics. Historically, the next thing that happened was Akka introduced futures. Back then, that was before Scala 2.8, Scala didn't have futures. So around 2012, I believe. And there was a bunch of future implementations. Actually, it was a bit messy because everybody had their own. So Twitter had their futures, Scala Z had their futures, Akka had their futures, Lyft had their futures. Everybody had their own future implementation. Because Scala, unlike Java, didn't have one in the standard library. You could use the Java future, but it's just not very good, because it forces you to block, right? And we want to do reactive programming, we don't want to block. So the Scala, Akka future / Scala future was exactly that. It's a non-blocking monadic future, and nowadays that's part of the Scala ecosystem. So the next thing, kind of we build one thing on the other, right? So the next thing is you have these asynchronous operations. So you need to maybe somehow stop them from executing because they keep failing. An example here is basically circuit breakers, right? So you have an overwhelmed server, you keep sending requests to it, it could be in futures, they blow up. So what you do with circuit breakers is, okay, you trip it to open, so then no further executions of that path will be made until the circuit breaker is closed again, usually via a timeout or something like that. And then you trigger the thing again. You only send one message. If it fails, it's still open and you will only send a new request in a few seconds or so, right? But, so that's nothing new. I'm sure you've seen circuit breakers with historics. We've had them for years as well. But the problem about them is you have this good system, you crash it into the wall, try to recover, then you crash it into the wall again, then you try to recover, and it's not very graceful. So remember this, because this is basically what initiated our thinking about we need to do something that's a bit more graceful than just trying, failing, and then trying and failing again. Am I trashing circuit breakers? No, they're perfectly fine, but they're not a replacement for proper flow control. They're good for handling failure. Okay, so if things really fail, things go down, we can do that. But it's not helping in the happy case where we want to control the flow of data to the optimum level. Because that's putting it to the crashing level, then restarting again, etc. So we can do better. And that's exactly what Akka Streams and interactive streams is about. So, quick side jump, because now we reached the cluster oasis. And we do that because to talk about more interesting things, we would like to talk about distributed systems. So the cluster does exactly that. It brings actors to a distributed setting. And when people think about actors, they often think about, okay, it's like a thread, but has this concurrency model, etc. That's true, but actors are a bit more powerful than that. They're really designed for distributed computing, because the entire idea of that you get a message is so easy to put on the network, as it is onto multiple threads, but it really would be a waste to not use actors in a distributed setting. You totally can, but locally there's a bit easier abstractions as well, like streams or futures. So, what the cluster does is basically membership, but that's by itself not very interesting. What the interesting bit is sharding. So we have something that's called a sharding manager, and basically it looks at the message type and routes it to the respective node and to the respective actor. So kind of like sharding in databases, but on alive and kicking entities that can send messages to one another. And of course, if one node fails, we notice, okay, this node has failed, let's migrate those actors to somewhere else. Let's migrate them somewhere else, so we can resume operations without any downtime. The one thing that could happen, a little bit of message loss in such a situation, but if you don't want message loss, then you make the sender at least once delivery, and it works. We also have tools for that. So it's failure detection with heart beating and some mechanisms to manage that. So then we stayed on the inside, right? That's inside your actor system, actors talking to actors, and it's all good and fine. But by the end of the day, you gotta reach someone else, right? And the someone else usually nowadays means HTTP. So that's what Spray was developed back then, and nowadays has been merged, we rewrote the thing, and that's Akka HTTP. So the interesting thing about Akka HTTP is we co-developed it at the same time as we did Reactive Streams, the Reactive Streams initiative, and Akka Streams. So it really is from the ground up built using streaming from the TCP layer to the highest level APIs. It also brings a fully typed HTTP model. So for example, in some other frameworks, you try to send an accept header or set the content type, and you put the string there. It's, I don't know, text JavaScript or something, text JSON or something, application JSON, or something like that. You put that as a string. We have that as types. So you can't possibly put a wrong thing in there. It's so good that even like competing servers just use this model, the one from Spray, instead of inventing their own. The HTTP for us uses the Spray model actually. As I said, streaming from the ground up, with all the fancy things like WebSockets and streaming and server-sent events, etc. Whatever you want. Now, since we developed this at the same time as we developed Akka Streams, there's a bit of a chicken and egg to explain what I'm showing you here. Because a flow is an Akka Streams concept, right? So we'll see what Akka Streams is in 1 second. But basically it means it's like a function, but it can do multiple elements, right? So it could, technically, and we do that in HTTP too, get one request and start pushing more responses. It's basically server-side push in HTTP 2, right? So that's what a flow is. It's something that can get inputs from one side and can emit things on the other side, kind of like a pipe. So we model the HTTP server not as a function, because other things like Finagle, they model the server as a function. So it's function from HTTP request to HTTP response. We model it as this flow, which allows us to fit nicely with the server-side push model. Which is also kind of, we were in this good situation that we were designing all of the APIs with that in mind, because it was new APIs, so it's nicely fitting. And the HTTP entity, on the other hand, is a source of byte strings. Byte strings is like byte arrays, but with some convenience methods. And that's a source. So a source is basically an Akka stream that has one output but 0 inputs. Right? Logical. So the interesting bit about the entity is we connect that all the way down to the TCP layer, and if you don't pull from this entity source, we eventually will stop pulling from the TCP connection. Which actually means that the TCP window mechanism kicks in and would back pressure the other side, the client, who's sending you a file. So by just using this type, basically allowed you to back pressure implicitly or explicitly any kind of client that's connecting to an API. I can show a demo of that if you're interested. The WebSockets are the same. Messages come in, messages come out. And if you've never seen the routing DSL, this is how the routing DSL looks in Akka HTTP. Very much like Spray. There's some changes, but nothing you would notice in a Hello World example. And that's a full server app. You have an active system that hosts the thread pools, the materializer, that's for Akka Streams. It looks at the description of your execution and then actually executes it. Right? So we always need to materialize something. The routing DSL and actually binding the server. So how people would deploy an Akka application is just have a main method, run your things. Usually not in containers, but you totally can. Not in application containers. But you can if you want. So that was the high-level API. Okay, so if the path starts with get, hello, and it's a GET request, then do this. There's a low-level API, if you want to have like completely full control, and it also shows this fully typed API that I talked about for the HTTP model. So the content types, here we use this Scala syntax with the ticks, so you can really just type the name as it appears as you know it from the browsers, and it is a fully typed object of text HTML with UTF-8. For example, you could not write just a media type here, because a media type is missing the encoding. If it wouldn't compile, you need to give it encoding as well. Is it UTF, is it ANSI, etc. So we have our insides kind of made up. We have clusters, we can do messaging between different nodes, we can communicate with different applications via HTTP. So let's try to improve the internals a bit more, because we didn't really talk about any kind of persistent state. Obviously, you can just use whatever database you want. It's, Akka is just an abstraction for concurrency and distribution. It doesn't forbid you to use any kind of database you want, including blocking ones. You just isolate them on a thread pool, perfectly fine. But again, can we do better than that with the assumption that we know we have these actors and they get these messages? And what does this remind us of? Well, basically that's event sourcing in a way, right? Because event sourcing means that you have persisted some events, and if you replay them, then you recovered the same state as you had before. In a really short pitch, what event sourcing is. So what we do in Akka is, actually the naming here is a bit funny. So Akka persistence initially was developed by Martin Grosser. It was then called event sourced. Then we took it over and worked with him to make it a bit more production ready, a bit more polished. And then it was named Akka Persistence, perhaps a bit unluckily because it is strictly about event sourcing and not about any kind of persistence with an SQL database or something. So it's a bit, sometimes people get confused by that. So, wording. The incoming messages that your actor gets, so that's an actor on a node, it gets some commands. So when we use event sourcing, or just CQRS actually, we talk about commands and events. So commands would be give me a thing, right? Do the thing. So they are imperative present tense. And events would be past tense and would mean something like I gave the thing, I started the process, events like that. So if we store things like that, and then a node fails, for example, it started doing some transaction, but it never got to finalizing it, then, okay, we just restarted it on another node, we know by its identifier that's the P1 process, and it would recover the events from the distributed journal. Distributed journal usually means, Cassandra, but can also be like 70% people using that would be on Cassandra. It's a perfect fit, etc. I also wrote one for HBase, not that popular nowadays, as you know. And there exist implementations for just an SQL store, or Mongo, or we also did one for DynamoDB. But that's, and Dynamo is a bit funny with pricing, because you pay for transfer, right? So it's kind of expect your traffic way more than your own database. And what we do in addition is, because, okay, this actor has restarted, we did the failover, but someone else is sending messages to this actor, right? So what we do is, because it's still recovering, this could take, depending on the size of your log, if you did snapshotting or not, this could take a while. So what we do is we buffer these messages until the actor has recovered. So it has replayed, for example, if it's a wallet actor, and we gave it commands like pay €5, pay €10, and then it has decremented its amount of money in the account. Then we only want to get a new commands to the wallet once it has remembered that it has paid out this €15 before, right? So first we replay all events. Once we have replayed the events, it's in a valid state again, and it can start processing the new incoming command. Again, completely transparent, you don't need to care about it at all. Just works. One difference, previously in actors we just had one receive block, so the function that is called when you get a message. In persistent actors we have two to separate where you should be doing side effects. Because you have the receive recover, so this gets invoked with the persisted events. And you shouldn't be doing side effecting, because that would mean for each recovery you would be sending someone money. Right? You don't want to send someone money during the recovery all the time. You want to do it either after recovery has finished, if there's outstanding stuff, or directly in when you get a command and you reply, okay, I will do this thing in the future. So that's the differences. So that was a bit pastish. Now the present and near future is, which is the second half of the talk. So, distributed data. Has anyone heard about Akka distributed data? Just 2 people. So now I think this is the new stuff for people who have not been tracking Akka very closely. So on the map here, here we have mount persistence, and here's the data fields of CRDTs. And they're close, and what binds them together is the cluster. So both make sense really in a clustered setting. And what distributed data is just a collection and implementation of the gossip protocol for disseminating conflict-free data types. Anyone heard about conflict-free data types? The same people who have heard about distributed data. That makes sense. So, the trade-off is that if you use Akka persistence, we have made a specific conscious decision about staying in this part of the realm. So it has to be partition tolerant. So that's the CAT theorem. You've seen it on conferences, I hope. The theorem is basically saying, okay, you can only pick 2 of these things, except this doesn't exist, and this doesn't make any sense. So yes, you can pick 2, but you always have to pick partition tolerant. Because if you build a system that's not partition tolerant and does whatever in a partition, then you've built a useless system. You kind of have to pick partition tolerance. And then you need to weigh one or the other side. Does it have to be always consistent? So that means you have to either have a centralized point to do all the decisions, or some kind of committing of the things. Or you can go with what we do in distributed data, is it will always be available, but it may have slightly stale data. So for a thing like a wallet, you probably want to be consistent, right? Should I pay out or should I not pay out? While actually ATMs do not stay on the consistent side. They actually sometimes optimistically will give you money. If you got too much money, the bank will get you. So in banking systems, it's actually more available than consistent. And then it's eventually consistent. So distributed data is available and partition tolerant. What that means is in persistence, we had this actor and it had the state. It is the wallet in persistence, right? It is the wallet, it makes the decisions, so it's always consistent. What happens in distributed data is we have a data type. So that's a positive-negative counter. So in distributed data and CRDTs in general, the data type has to support certain kinds of operations, and it's not trivial to just invent random data types, so it will be convergent like that. So a counter like that, it can be written to from any number of threads and nodes in a distributed system, and it will be always eventually consistent. So if you add 5, then you remove something, or add something else, and then while you were doing that, I also was updating that counter. Once they converge, these 2 data points, the result will always be the same. The count will be always correct. But eventually, once they get together. So the API is actor-based. So if you want to modify the counter, you send basically a request to write to it. And you also say, okay, the write consistency should be, okay, 2 nodes should see this write within 3 seconds, otherwise it's a timeout. So it's a different way of thinking about applications. You think about the data and how it's disseminating in the cluster, and not as much about the entity. There will be some entity somewhere using this data, but it's not the entity itself. Obviously, because we talk about the dissemination here, there's different levels at which you need to do such a write. And again, it's a trade-off between consistency and availability. You can return from a write as soon as you can if you just write to the local, right? It's trivial, you write local store, and then it's done. However, if that node then fails, then you've lost the data. Usually you'd write to the majority, also referred to quorum, and then you can tolerate at least n by half minus 1 failures. Or you can write to all, so that's consistent, but it will take a while to reach all the nodes and everybody has to confirm that they've seen the write. So you can tune what kind of guarantees you want for each of the writes. So, finally streaming. So, a funny side story is that basically, you remember back there when we did futures and circuit breakers, and it kept always kind of lingering in our brains that we should do something better. And then, with the Play guys, we had a discussion that we should do something because they had a really difficult API and the users were struggling to use it. And we had a really low-level API, so from that sense people were struggling to use it. And then we talked with Ben Christiansen, who had a nice API but didn't, at that point at least, think much about the back pressure. And we got together and basically started the Reactive Streams initiative, which I will fast forward a bit. Because that's not really, that's Reactive Streams. Okay. So it's a building block, it's not an end-user API, and this will be known, and currently is known already, as the Java util concurrent flow interfaces, and there's not really implementations in the JDK except one example implementation, and that's because it's supposed to be a spec, and many people, so Akka, Red Hat, think of Vertex, Spring is now implementing that as well in Reactor, and many other people like the MongoDB drivers, everybody is implementing Reactive Streams. So, we have this now included in the JDK, many people are implementing it, but what does it actually do? So it solves this problem. If you think about this circuit breaker case that I was complaining about, it's not very graceful. It's basically that. Someone is processing things slow, someone is sending things fast. How do we control that? And basically we control it by figuring out what to do if there would have been an overflow. One solution to overflow, which you can basically do by flipping a switch in Akka, is drop messages. People always freak out when I say, yeah, just drop the messages, but that happens over time. Kernel does this, network infrastructure does this. But when we talk about application level messages, people are not so comfortable with just dropping messages. Although any kind of higher level guarantees will be building on dropping and redelivering things anyway. You could increase the buffer size, but the buffer size is always limited because memory in our computers is limited. So what do? Basically we make this really simple protocol that works on a permit system. So if you know your buffer size and you're processing this queue asynchronously, and you know how many slots you have, you can advertise to your upstream, okay, I am ready to consume at most 3 elements, and the upstream is not allowed to send more than 3 elements until it gets more permit. That's it. That's basically Reactive Streams in one slide. Not very difficult when you spell it out like that. API looks a bit Rxy. However, the tricky thing is really the semantics around it. So we have our goals, and the big one is really important. It's for interop. It's not for everybody implements their own. It should be more like we try to connect them together. But the tricky thing about Reactive Streams is not the API, which is 7 methods. It's all of the concurrency rules which you need to basically watch out for when you implement such a thing. So instead of everybody implementing their own, you should be using like Akka Streams or Reactor or RxJava 2, because in one they still need a bridge. That's because binary compatibility goes for them. API, very simple. I'm sure you've seen that. Looks a bit like Scala collections, looks a bit like Java Streams collection operations. However, I would like to kind of highlight that streams are not supposed to be collections, so that's a completely different thing. And sadly, Java has used the word stream for doing stuff on collections. which is a bit unfortunate, I think, because when we talk about streams, at least in these kinds of systems, it's usually about infinite, unbounded, and eventually the data will get there kind of things, and not a collection, which is you have the data in memory. Very different beast. So, the only thing you need to remember from Akka streams here is really that there's these certain shapes. Source we talked about, that's an HTTP entity, for example, that's an HTTP server, or just a map function, and the sink, obviously, where the data flows to. Okay. So, let's look at HTTP 2, because basically, okay, Play Guys and we and RX and other people, we did this reactive streams. Now, what can we do with it? Okay, I already told you that we did an HTTP server with it, but what more can we do with it? So, with HTTP 2 and modeling the server as a flow, so for one incoming request we can send multiple output responses basically. It fits really nicely with the HTTP 2 model actually. But what people really want HTTP 2 for is basically saving on connections a bit. So imagine you have an API that serves two kinds of images. One is a bit bigger, one is a bit smaller, 1 meg, 2 megs. And this is how a request looks, well, how loading such a page looks on HTTP 1. Right? There's a lot of stalling. So all this gray stuff is basically connections waiting, because it's gonna be one by one, and the limit of connections at the same time is 4 or something, at least in this example. And the load time around 5-6 seconds. And I'm doing this on an API that makes it specifically slow to server requests, so you can just slow down serving the data. So it takes a few seconds. And also, each of the connections that will be opened to the server will take the SSL handshake hit, right? So that's also something to consider if you really want a low latency thing. How does that look on HTTP 2? Basically one connection, all the requests can be sent at the same time, and then we start pushing the data. How we push the data can be influenced a bit by the client. It can say, hey, this stream has this and that priority. However, it's really up to the server to figure out the best way to push stuff. Without any fancy implementation, this is just pushing as fast as we can onto that connection. We already, not quite half, but we shave off 1/3 of the response time here to get the entire page. Number of requests, transferred data, but that's all the same, right? Obviously. It's semantically the same operation. Now, we'll get to what that actually means for play, because what we'll be doing in Akka HTTP is actually not much. We will just do all the low-level details for it, but we won't be doing, hey, smart server push thingies. That's not at all something Akka should be even looking at, because we don't have enough information about what we should even push. And that will be actually very tricky to figure out for frameworks in the future, I think. So, one of the last topics, which is Akka Typed, the typed woods. So, the number one complaint about Akka and Akka actors has always been that the actors are untyped, if you want to call it like that, because an actor can receive any kind of message, including messages that it cannot handle. If you send an actor a message that it cannot handle, it will be dropped into the dead letters queue. You'll get a log statement saying, hey, probably something's wrong, you sent this message and it's not being handled, but that's about it. And we'd prefer to maybe have a compile error, right? It's a Scala after all, it's Java after all, we have type systems. The reason it didn't initially is it's very much Erlang inspired, right? And if you ask an Erlang person about, hey, how do you live without types in your concurrent apps, they don't even bother. And to be fair, it's not that super difficult, but yeah, I understand the complaint. So we actually have been working on it for a number of years. First initial API was typed actors, which was basically looking like a Java interface. which is kind of betraying everything we stand for, because we say, okay, don't do RPC, right? And what is that? Yeah, that's RPC. So that exists. When Jonas and Victor implemented that back then, it was basically to lure in people who were too afraid of Akka but kind of knew Java to at least give it a look. So don't use that. Okay. Second attempt, so to actually do something that would make sense, was typed channels. Roland Kuhn implemented that. Sadly, you can tell probably already by the types here, it gets really complex. So the typed channels, we dropped that a number of years ago, like 2-3 years ago. Too complex, had to rely on macros to actually deliver the promises it made. So we dropped that. So over the last 2-3 years, we've been thinking about it, and a few white papers came out. The reactors from Alexander Prokopes and Martin Odersky also were very interesting and inspiring for us. We did a few prototypes, especially the things we learned in Akka streams kind of led us to understand what we can pull off in types in concurrent systems as well. So finally we have Akka Typed. You can try it out. It's currently a snapshot, and it has 2 styles of actor, which I want to show you right now. So the key difference is, yeah, that the actor F has a type. I mean, 3 characters of difference, but actually makes a huge difference. And everything is a behavior. So we'll be talking about behaviors and not, you want to be extending actor. So the actor is the thing that runs the behavior. So it's a change of mindset in that sense. And if you compare the two, a normal untyped actor on the left, you see, okay, no type parameter, this can match anything it gets. And on the right, this is the mutable style. So it's a mutable behavior of a certain type. And then on a message it gets this command and can only get these types of commands. The second style of API is an immutable one. By immutable we mean you don't even extend the class, right? In the mutable one you still extend the class, it can have fields, you can modify the fields. What we do in an immutable actor, it's not that it doesn't do anything, it's just that it doesn't have fields to store the state in. What it does instead is, at the end of each expression, this is a return. If you don't know Scala, last line in a branch is basically a return. So that's a return greeter behavior. Okay, what's greeter behavior? Ah, that's myself. So basically you become a new behavior that has an updated state. And this way we keep returning new behaviors. And we have some specialized ones like actor same, which basically means, yeah, I'm still the same actor, still the same behavior. So, as you see, everywhere in Akka there's a lot of pattern matching. And for good reason, it's really, really useful. It helps you to deconstruct all these values very easily. And it also gives you warnings, actually, because now the compiler knows, okay, so this message, that's a command, and if it had like 3 message types that extend command, but you only matched 2, the compiler can tell you, hey, you forgot to match this 3rd message type. So Java's getting there. It's very nice to see Scala features like slowly creep into Java. That's actually a nice thing. I think that's very cool. So, but currently we don't have that, so we need to emulate that a bit in Java. So we have a builder that does onMessage. Okay, so if it's this class, then do this. So we emulate that a bit. Java will get there eventually. If you want to try it out, we're currently in a mode that's basically gather feedback mode. That's why the funny repository and funny name. We don't want to commit any compatibility guarantees to it yet. But please have a look. There's some excellent blog posts about it. And I think I'm out of time. But here's an alpaca farm. And you probably can guess the wordplay, right? It's like a camel, but not really, and with 2 Ks. So in the few minutes I have remaining, I'm cutting into the questions time, I think.
Yes, we can have some questions.
No, I think I'll just steal 5 minutes from the questions, okay?
Okay, do it.
Yeah. Okay. So Alpakka is basically what Camera kind of wants to achieve, but we want to achieve that in the reactive streams ecosystem. So we implement, and the community implements, and a lot of people have implemented various connectors to stuff, including, Kafka, some queues, some databases. And because this is all reactive streams, yeah, of course, it's going to be implemented in Akka streams, but we kind of contribute to the grander ecosystem that even if you don't use Akka streams, but you want this connector, you can use whatever you want. You can use RxJava to consume whatever sources or things we provided here. It's still added value for everyone in the field. So, explaining it in 20 seconds again, you have these building blocks, they just fit. Killer feature without much additional work. You just stay in the reactive streams ecosystem. So you have a flow that fits, the types just fit, you can exchange it to a source and sink, still fits. And the interesting thing is, okay, it's not about just the types fit, that wouldn't be interesting. It's about the concurrency model that is guaranteed by reactive streams. So you know how these will behave. They will never overflow you if you don't request data from them. Really, this ecosystem is kind of the killer feature of reactive streams. It's not a single library that is the killer feature here. Okay, one of the last things. So the Artery here. The Artery is our new remoting implementation. It's a bit more than we changed the transport to Aaron. Some people like to just say, oh yeah, Akka is now based on Aaron, and they didn't do anything. We actually did a lot of work in there. We have dedicated lanes for prioritized messages. We have dedicated lanes for big messages, so we don't stall the other ones. And in steady state, it's basically not allocating anything, because Akka streams get fused, all of the writing that's using pooled byte buffers everywhere, all of the actor refs, manifests, everything is pooled and cached. So in steady state, the write side doesn't allocate anything. The receiving end, yeah, it will allocate because it deserializes the thing, right? So it kind of has to give you the thing out of the byte buffer. And we do compression. So that's a normal message in normal Akka remoting. It has a lot of metadata about where it's sending to, right? So, okay, I'm sending to system something something on this address, this actor. I'm sending to the lightbulb. Right? That's a lot of text. And that's a bit wasteful. So what we did is we implemented a way to detect which actor would be most efficient to compress, basically detecting heavy hitters, which actors are most chatty, and then we compress those to int identifiers. So basically we saved all of the strings which you had here. That's one. Forgot which fields. You get the point. And the message remains the same. Here's a hello, here's a hello. But percentage-wise, the amount of space we saved for small messages, that can go up to like 80%, because if the message is small, the metadata was completely dominating the message size. And this is a request, not a feature. So we're currently looking at, we're working with a lot of customers that have requirements about globally deployed things. And we're looking into how to help them out. So if you have use cases that you have multiple data centers, let me know. We have some ideas what people may want, but at the same time it's also a bit tricky to implement generically. They'll skip over the extras. It basically means we have monitoring, we have tracing, we have Zipkin support. IntelliJ support is coming. So if you didn't notice, IntelliJ is getting Akka features now, so that's also very exciting. There's a .NET port, a JavaScript port, and here's the link for the book. If you want to give it a read, it's like 20-30 pages, nothing really fancy, but if you're new to this stuff, it may be fun. Credits and questions. I hope this was useful.
Maximum 2 questions. with quick answers.
Yes, please.
Thanks. One question, there was a slide about that sender was a pain and it is gone.
Yeah.
In Akka Typed, how it will be, how this ask and reply pattern will be replaced with what? What will be the scenario?
Yeah,
Thanks.
good question. Let me show that slide so you can see what we're talking about. So basically, the sender was a magical variable in Akka where you know who sent you a message. The thing is, sometimes you don't need the sender, but you pay the price for it anyway. And it's not safe to access from a future or from a different thread, and people would get that wrong all the time. So actually removing it helps to resolve those problems, because no sender, no problem. How do we resolve it is basically, so that's my message, who to greet. There should be actref. I'll just show very quickly what I want. Okay, I forgot that's not actual text. Okay, live sliding. So basically, you pass along reply to, and this makes a lot of sense because sender wouldn't know the type, what it's expecting. So now you can say, okay, reply to, and I want a greeting. That actually fits very well, and it's also more explicit in the messages. You know what kind of reply they want.
Questions. Okay. Thanks, Konrad, a lot for your talk. People are getting nervous because lunchtime is approaching.
Yeah, let's do lunch. And if you have any questions, just grab me. I'm around here until 4 or something. Sadly, I have to leave today. So yeah, see you. Thank you.